Good morning. Today let's continue on the three-phase AC circuit analysis. So as we discussed last lecture, there is 3 wires or 4 wire systems based on for the three-phase systems. So 3 wires where the neutral does not exist or the neutral conductor has been removed, or 4 wires where the neutral exists. Then we used to discuss about 4 currents, 4 line currents, IA, IB, IC, I neutral, and we discussed about 6 voltages, 3 line to neutral, 3 line to line, such that VAN, VBN, VCN, those are line to neutral voltages, VAB, VBC, VCA, those are line to line voltages. Then whenever we have 3 wires, then the neutral does not exist. So when you have any 3-wire system, basically you will have only 3 voltages. There is no neutral. So you will have only phase A, B, C. Then you will have only 3 voltages. Those are based on VAB, VBC, VCA. And you have 3 currents, 3 line currents, which is IA, IB, IC. Those for the 3 wires. While if you are dealing with 4-wire system, then it will be as there will be 6 voltages, 4 currents, I, B, C, and in neutral. So there will be VAB, VBC, VCA, in addition to VAN, VBN, VCN. So 6 voltages. And there will be 4 line currents. Those are IA, IB, IC, and I neutral. And keep in mind, I neutral will be 0 if and only if balanced system. If it is unbalanced, then the neutral currents, it will be non-zero. And I mentioned as well, the 3 wires most likely been used on high voltages, extra high voltages, when we transmit the power for very long distances, where I can guarantee the system is balanced and I can make sure there is no connection in the middle. So I'm transmitting the power for 100 miles, 200 miles, whatever. Then there will be no unbalanced situation. So during the transmission, to get a cheaper cost, it's better to have 3 conductors. While in the distribution, you need to be 4 wires. Why? Because sometimes in distribution, it's based on single phase. So when you supply power to your home, supply power to your neighbor, your other neighbor, you are in phase A, your neighbor phase B, the other neighbor phase C, we cannot guarantee all of those are balanced. Therefore, if it's unbalanced under 3 wires, this will cause a lot of problems. Then to solve this, of course, we will need to use single or 4 wires. Then we mentioned how about the source connection or the load connection. We mentioned there are 3 types of connection depending on how many wires do I have. So there is Y connection, there is delta. Y connection, there are 2 things for Y. Y with 4 wires, Y with 3 wires. In either situations, for Y, no matter if it's 4 wires or 3 wires, the neutral exists. So in 4 wires, there is a neutral wire, a neutral conductor that supplies source, connected source to the load. In the 3 wires, Y, the neutral still exists, but we don't have a conductor for the neutral. Then we have a 3rd type called delta, whereas the neutral does not exist at all. So basically, when we look at the 4 wires or 3 wires, both of them, they have 6 voltages. Even though it's 3 wires, but it can have 6 voltages because the neutral exists. So we will say we have VAN, VBN, VCN. Then we have VAB, VBC, VCA. Okay? Because all of them exist. All the neutral exists. Therefore, we have 6 voltages. Regarding to the currents, the situation can be different. So here we have IA, IB, IC, and we have I neutral. Therefore, in 4 wires, we will have 4 currents. 3 wires, we will have only 3 because there is no neutral conductor. Okay? Okay, does this make sense? Now, in delta, the situation is different. In delta, the neutral does not exist at all. Therefore, we will have only 3 voltages. What are these voltages? VA, B, VBC, VCA, whatever. VBC, VCA. Those are 3 line-to-line voltages. The neutral does not exist, then the line-to-neutral voltages that we used to say, the 3 line-to-neutral voltages are not, they will not be exist because there is no neutral. So we have only V line-to-line. So we can see that delta, again, it's connected as a delta shape, and it can be in different shapes. So it can be like this. For example, here, as I mentioned, delta to delta. This is delta shape. So basically, you can see how it looks like here. So you can either draw it the symbol delta, or you can draw it like this way. And the same thing for y. You can draw it as y, like this shape, or you can draw it as y with this shape. Either way. Now let's go to the notes. So this is the Y connection with 4 wires. So for this course, to make it much easier for you, we will not go through 3 wires delta. 3 wires delta exists, but let's make this course simple, so we will not include the 3 wires delta. So whenever we see Y, we will assume it every time it's based on 4 wires. So that's how it looks like. This is the source connection. This is the load. In order to maintain a balanced operation, there must be the load identicals. And for the sources, there must be the same voltage source, the same magnitude, but the difference is the angle with phase shift 120 degrees. Okay? Again, this delta can be, the Y can be drawn like this way, or can be drawn as a Y. So here is a neutral, A, B, C, whatever. Then when you have conductors, here is the conductor for each one. Again, Y, here we will have 6 voltages. These 6 voltages are based on 3 line-to-line, 3 line-to-neutral. So line-to-line VAB, VBC, VCA, then here V line-to-neutral, VAN, VBN, VCN. Then the next connection, delta. Delta here, we don't have a neutral, therefore we will have only 3 line-to-line voltages. So delta again can be drawn like this shape, or it can be drawn as a delta shape. Okay? So the neutral does not exist. Then therefore all of the voltages that we have are based on VAB, VBC, VCA, which is VAB, VBC, VCA. We don't have a neutral, therefore in delta connection we cannot say there is line to neutral, or we cannot say there is 6 voltages. There is only 3 voltages because the absence of the neutral will eliminate the remaining. Now, regarding to the currents, in 4 wires we have IA, IB, IC, I neutral. That was in Y. For delta, again, sometimes as a shortcut I can write delta instead of delta, and here Y as a Y simple. In delta, we have 3 line currents, IA, IB, IC, and there is something also that can be, there's other currents that we need to take into consideration, which is the inner currents, which is this currents, this currents, this currents. Or in other words, in the sources, this currents, this currents, this currents. So we have 3 new currents that they didn't exist in Y. We have them in delta. That's currents, this called inner delta currents, or sometimes as a shortcut I'm calling them delta currents. So we have delta currents, which is the currents inside the delta. Again, those were not exist in Y, now they are existing in delta. So these currents are IAB, IBC, ICA. So 3 delta currents. And in addition to this, we have 3 line currents. These line currents are IA, IB, IC. So as a result, whenever we deal with delta, we have 6 currents. Then in summary, you can notice why there is 6 voltages, 4 currents. Delta, 3 voltages, 6 currents. So almost like the opposite. But I would say like 4 currents, because if you assume the neutral is 0, then you can say 3 currents in Y. While in delta, you will have 6 currents. So these 6 currents, 3 line currents that we know for the conductors, and the inner delta current, or the inside delta, or the delta currents. Okay? Is it clear? Now the question is, how to calculate these delta currents? How can I calculate this based on the line currents, based on IA, IB, IC? You can do KCL, right? So we can do KCL to calculate these currents. So these formulas, IA equal IAB minus ICA, so notice A here, A at the beginning, A at the end. So IBC, B here, so it will be IB equal to IBC minus IAB. So you notice B, simples how. Then ICA, or IC equal ICA minus IBC. So you can memorize it actually easy. Basically, IA equal to the first one starts with letter A, IAB, then minus the second one ends with letter A, ICA, and so on for IB and IC. So keep in mind these 3 equations are the general equations that are valid anytime, even if it's unbalanced. Recall when we discuss about line-to-line voltages, VAB equal VAN minus VBN, and so on. So I mentioned like those general formulas that can be valid no matter if it is balanced or unbalanced. And after that, I said that VAN can be square root of 3 angle 30 times VAB equal square root of 30, square root of 3 angle 30 times VAB, or times VAN. Therefore, when we discuss this, if we said it will be valid only if and only if the system is balanced and positive sequence. So the same conditions that we used to do for the VAB, VBC, VCA, we can do it also for the delta currents. So just as a recall the line-to-line voltages, I said that VAB equal VAN minus VBN. Those are the general formulas that can be valid anytime, no matter if it is balanced or unbalanced. Then we went through a special case by assuming unbalanced and positive. So VAB equal root of 3 angle 30 times VAN. That's what we discussed before. Then we said that if it is negative sequence, it will be angle negative 30. That was when we discussed about line-to-line and line-to-neutral voltages. Now, we have line currents and delta currents. There is a similar relationship. So those are the general formula that are valid anytime, no matter if it's balanced or unbalanced. Then we have a special case if it is balanced and positive sequence. And another formula if it is balanced and negative sequence. So we can say that IA equal to root of 3 angle negative 30 times IAB. IB, the same, angle times IBC. IC, root of 3 angle negative 30 times ICA. So those can be easier or as to get to calculate the currents in easy way, but with less complication, or less mathematical calculation. But keep in mind, you need to make sure if it is positive, use the equations with positive. If it is negative, use the equations with negative. If you are unsure, if you are after to make mistakes, or I'm not sure is it positive or negative, or should I use this or not? If you are unsure, use the general formula. And this will be fine. Then the negative sequence, if it is negative sequence, it will be angle positive. Okay, so there is here sometimes something that can make a confusion. What do I mean by confusion? Let's go to the line-to-line voltages. When it is positive sequence, we used to put angle positive 30 in line-to-line voltages. When it is negative sequence, we used to put a negative, right? But when you go to the currents, it's the opposites. If it is positive sequence, we will put negative. If it is negative sequence, it will be positive. Okay, how can you make sure that we are doing this in the right way? Recall V times I conjugates, right? We know like the power is V times I conjugate. So you can say that, do the conjugate for the currents. So when dealing with the positive, if it is positive sequence, you will say positive 30. Then for the currents, since I'm doing the conjugates, the conjugate of the positive 30 will be negative 30. Then that's it. For the negative, regarding to the voltage, it will be negative. Regarding negative sequence, so the angle will be negative 30 degrees. Now let's go to the currents. When you do the conjugates, the conjugate of negative 30 will be positive 30. That's the way that you can imagine. Again, let's discuss about like the voltages, the currents, then balanced and positive sequence. So it will be square root of 3 angle 30 degrees. Then for the current, square root of 3 angle negative 30 degrees. Then balanced and negative sequence, root of 3 angle negative 30, while there root of 3 angle positive 30. So just keep in mind the angle sign are different. Okay, any question? So now we have too many formulas. You don't need to memorize any of those. You can write them in your note sheets. And the other thing, which is just try to understand it. Even sometimes, if you understand it very well, you don't need to write it. If you know, like VAB equal VAN minus VBN, okay, that's it. IA equal to AB minus ICA, because A in the beginning, A at the end. Then if you just understand how we deal with this relationship, then it will be fine. Now, let's go in, so for example, in summaries. Whenever we deal with voltages, there are 6 voltages: line to neutral, line to line. The currents, there are 6 currents: line currents, delta currents. Now, if we are dealing with Y, then we will have 6 voltages, 3 currents, or I can say 3 or 4 currents, depending on the neutral. Whenever we deal with delta, we have 3 voltages, 6 currents. Just keep this in mind. Okay, does this make sense? Any question? Okay. Let's go to this example. Given a 12.47 kilovolts 3-phase system, find all of the 6 voltages. Okay, what should I do? Recall our standards in the 3-phase system. Is there any information about the sequence? Say like this is positive sequence or negative sequence? No information, right? So the default is positive sequence. The other thing, is there any information says the system is balanced or unbalanced? Or is there information about the 3-phase voltages, or the loads Three-phase load, so I can need, or I need to determine is it balanced or not? Nothing, right? No information. The only thing that I have is the voltages, 12.47, right? So since there is no information, so the other thing, which is the default, is balanced. The other thing, how about the 12.47? What's this voltages? Is this line to line, line to neutral? What do you think? There is no information about it. So the default is line to line. Line to line voltage. Unless it's mentioned this is VA and VBN, or this is the voltage of one of the phases, unless there's a statement asks you is it balanced or not, or if there's any other information. But based on this statement alone, it is just says 12.47 kilovolts and just, that's it. I know it's three-phase, 12.47. Therefore, it's positive sequence. The default, it is balanced. This is voltages line to line. This is line to line magnitude. Not, of course, not the angle. Now, what should I do? How can I deal with this thing? Is there any other information says assume or the or the angle of phase A is something? Or is there any information says that you need to determine the angle of phase A? No information about it. So the other thing, the default is phase A with angle 0. Basically, phase A as a reference. So what should I do? So remember these procedures. We will do it 100 times. We have V line to line given as 12.47 kilovolt times 10 power 3 volts. Then we need to calculate V line to neutral. So V line to neutral is actually V line to line divided by root 3. So we need to calculate 12.47 divide times 10 power 3 divided by root 3, which will be 7.2 kilovolts, or times 10 power 3. Okay? That's the first analysis. The second thing, let's start with phase A. So VAN equals to V line to neutral angle 0 degrees. That's the defaults. Ampere. I'm sorry, it's volts. Now, I'm going to write it here. Don't have space. So VAN will be 7.2 times 10 power 3 angle 0 degrees volts. So the next thing, which is how to calculate the other voltages. I just calculated one, VAN. So remember, the default is positive sequence, A, B, C. So A with angle 0, C with negative 120, B with negative 120, C with positive 120. So how to calculate VBN? VBN equals to VAN times 1 angle negative 120 degrees. So it will be the same magnitude, 7.2 times 10 power 3, angle 0 minus 120, it will be negative 120 degrees volts. How about VBN? VCN? VCN will be VAN times 1 angle positive 120 degrees. Then it's going to be 7.2 times 10 power 3 angle positive 120 degrees volts. So this is 1, 2, 3 voltages. I calculated the first 3 voltages, which is 3 line to neutral voltages. The next thing, since I need to have the 6 voltages, I need to calculate VBC, VCA, VAB, VBC, VCA. So how to calculate VAB? You have the general formula, which is VAN minus VBN. That's one way. Or you can say it is actually, since it is balanced and positive sequence, you can say VAB equals to square root 3 angle positive 30 degrees times VAN. So in summary, or as a result, it will be root of 3 times 7.2, which is 12.47. 12.47 times 10 power 3, angle 0 plus 30 degrees, it will be 30 degrees volts. So this is VAB. Now, how about VBC, VCA? how to calculate VBC. You can say VBC, it is actually VBN minus VCN. Or you can say root of 3 angle 30 degrees times VBN. That's the other way. Or there is a third way. You can say, since it's positive sequence, so ABC, here's with 0, negative 120, positive 120. This yields VBC to be VAB times 1 angle negative 120 degrees. So just subtract the angle negative 120 degrees. Then it will be 12.47 times 10 power 3. Angle 30 minus negative 120 will be negative 90 degrees volts. How about VCA? VCA, I'm going to find it in the fast way, which is root of 3 angle 30 degrees. Or actually, no, there is a short way, which is VAB times 1 angle positive 120 degrees. So it will be 12.47 times 10 power 3. So 30 plus 120 will be 150 degrees volts. Then this is third or fourth, fifth. Now fifth and sixth. So I calculated the 6 voltages. So keep in mind, sometimes there are 3 different ways here to calculate VBC, VCA. There are 3 different ways. All of them are correct. You can use the general formula. You can use the formula associated with balance and positive sequence. Or you can say, I don't need to do the calculation. Since A, B, C are just separated with 120 degrees, then the same thing will be for VAB, VBC, VCA. They will be separated with 120 degrees. Okay, any question? Okay. Now, so far, we did the 3-phase as a voltages or as the currents. The challenge is how to deal with the 3-phase circuits. How can I solve a 3-phase circuits system? Let's assume this example. Given a 480 volts 3-phase system, find all of the currents if the load is Y connected with an impedance 8.66 plus J5. And the second question, repeat if the load is delta connected with an impedance 25.98 plus J15. So how can I deal with this example, these circuits? Let's try to analyze the circuit. So we have a 480 volts. No other information about it. Is there anything says this is line to line or line to neutral? No. Is there any information about the sequence? Assume it's positive or negative sequence, or you need to find the sequence? No. So the default is positive sequence. The default phase A with angle 0. The default is this voltage is line to line. So what should I do before analyzing anything? I'm going to say V line to line will be 480 volts. So V line to neutral equal V line to line divided by square root of 3. So it will be 480 over root 3. This will be 277.1. Then I can say VAN equals to V line to neutral angle angle 0, because this is the phase. We'll pick it as a reference. So 277.1 angle 0 degrees volts. So I just calculated VAN. So we will do this every time. When we see any example, 3-phase example, we will do this. So these procedures are our standards. Now, the next thing is we need to imagine how the circuit looks like. So we have a 3-phase sources connected to the 3-phase load, Y connected with a neutral. So again, we will assume every time the neutral is connected. So how can we imagine the circuits? We can imagine it like this way. Here is a source. Here is a source. Here is a source. So this is the circuit. This is VAN, VBN, VCN. And we just calculated VAN as 277.1 angle 0 degrees. Okay. Now we have a 3-phase circuit. So we need to calculate IA, IB, IC, I neutral. So there is a procedure that we can do to make the problem easier. I mean, to deal with this, I need to calculate IA, IB, IC. So what should I do? Do I need to do KVL here, KVL here, KVL here. This might take a long time. So there is a simple procedure that we can apply, but we need to keep in mind if the system is balanced. If the system is balanced, so what we can do, which is converts three-phase to single-phase. So three-phase means three-phase to single-phase by finding or find the equivalent circuit, per-phase equivalent circuit, per-phase equivalence. Keep in mind this is true if and only if it is balanced. So what do I mean by per-phase equivalent circuit, which is, in other words, take phase A as a reference. Phase A as a reference. In other words, eliminate phase B, phase C, just assume that we have phase A. How does the circuit looks like if you have only phase A? So converting this circuit into a single phase, from three-phase to a single phase, this is called per-phase equivalent circuit. So I'm going to do convert three-phase to single-phase. So how, again, the three-phase or the single-phase looks like? I'm going to take only phase A as a reference. So I'm going to take this with the neutral, like the thing that's in yellow. Okay, let me redraw it. VAN 8.66, J5 ohms, this one, then IA. Okay. That's the per-phase equivalent circuit. Now, can you calculate IA? Do you know how to calculate it? We know VAN 277.1 angle 0 degrees. It is single-phase problem. We know how to deal this. In chapter, you can go back to chapter 5, I think. Yes, chapter 5. So how to calculate IA? Can you tell me how?
Equivalent impedance. Take the equivalent impedance.
Take the KVL of the impedance, basically. We can do Ohm's law, right? Ohm's law, or you can do KVL, whatever more convenient for you. So we can say IA will be VAN over the impedance. So VAN, which is 277.1 angle 0 degrees, divided by Z equivalent, which is 8.66 plus J5. Then when you do this in the calculator, it will be as 27.71 angle negative 30 degrees amperes. This is IA. Okay. Now, I just calculated IA. Remember, the question says find all of the currents. So how to calculate IB, how to calculate IC? What do you think about IB and IC? Do I need to do the equivalent circuit for B like this? I'm sorry. For B like this, for C like this? I think there is no need. You can calculate it in an easy way. Recall, the system is balanced. Balanced means same magnitudes. How about the angles? 120 degrees, right? So the default, it is positive sequence. So I will say this is, here is A, B, C. A with 0, B with negative 120, C with positive 120. So we can use this nice result since it is balanced. Then IB will be IA times 1 angle negative 120 degrees. Okay? So it will be the same magnitude, 27.71 angle negative 120 minus 30 will be negative 150 degrees amperes. This is IB. Then I don't need to do the analysis of the circuits. I just calculate IB and that's it. IEA and that's it. So IC will be IA times 1 angle positive 120 degrees. Keep in mind, I make it positive or negative depending on the sequence. Since it's positive sequence, that's why I did this. If it is negative sequence, just swap between them. You know, ABC or ACB. So it will be IC will be 27.71, negative 30 plus 120 will make it positive 90 degrees. This is IC. Okay? That's easy. In summary, whenever you deal with three-phase AC circuits, if it is balanced, convert three-phase to single-phase by something, and as we call it in electrical engineering, we call it per-phase equivalent circuit. Find the per-phase equivalent circuits. Again, we can do this if and only if it is balanced. If it is unbalanced, we cannot. You need to do KVL, KCL for the three-phase. Yes? Do you mean the question here? Yes. So we have a voltages, 480 volts, three-phase system, find all of the currents if the load is Y. Okay? Any question about this? So we can deal with the circuit no matter if there's elements in series, elements in parallel, just pick up phase A as a reference and that's it. The other scenario, or which is the second example, repeats, but the load is delta connected. Okay, what should I do? If the load is delta, there will be a challenge. Okay, let's go to the load. So the first thing about the voltages, VAN, will be the same procedure. 277.1 angle 0 degrees. There is no problem with it. But now the load is delta. So here is how the load looks like. And I'm going to draw the source. This is VAN, which is 277.1 angle 0 degrees. This is VBN. This is VCN. Okay, the load is delta. It is three-phase problem. The load is delta. So according to our procedure, let's convert three-phase to single-phase. Are we able to locate phase A? To say isolate phase A from the circuit? Someone can say, okay, this is phase A. Okay, where should I go? This way, this way. Can we find the per-phase equivalent circuit whenever we have this? The question is no. Or the answer is no. So what should I do? Whenever we have a delta, so that delta causes a problem. That problem is I cannot find the per-phase equivalent circuits. What should I do? The key is there a way to convert delta to Y? Yes, there is a way. Even if you go to the next step here, next slide, you will see Z delta equals 3 times ZY, or ZY will be Z delta divided by 3. This is important formula. So we can say the impedance can be converted from delta to Y. So what? Let's convert this from delta to Y. How to convert delta to Y? So we have Z delta is given as 25.98 plus J15. So let's find ZY. ZY will be Z delta divided by 3, which is 25 plus J15, 25.98 plus J15 divided by 3. So the answer will be 8.66 plus J5 ohms. This is ZY. Then, what should I do? Redraw the circuits, write it as delta. As a Y, I'm sorry. So here is VAN, and write it as a Y with 4 wires. VAN, 8.66 J5, VBN, 8.66 J5, VCN, 8.66 J5 with the neutral here. So what I did, I converted delta to Y. Delta load to Y load. I converted the load, not the source. The source is already Y. Okay? That's the first step, convert delta to Y. Then the second step, since it is already in Y, can I find the per-phase equivalent circuits? Yes, I can. I can isolate phase A as a load. Look at the yellow area. So the next step will be converting three-phase to single-phase by picking up phase A as a reference. Here is VAN 8.66 J5 like this. Then let's calculate the currents IA. Okay? So this problem now will be similar to the previous one. How to calculate IA? IA will be VAN divided by Z equivalents, which is VAN 277.1 angle 0 degrees divided by 8.66 plus J5, so it will be 27.71 angle negative 30 degrees amperes. This is IA. Now to calculate IB and IC, those are easy because it's positive sequence, so it will be the same magnitude, 277.1 angle negative 120 minus 30 will be negative 150 degrees. Then the last one, the same magnitude, 27.71 angle negative 30 plus 120 will be make it negative 90 degrees amperes. Then that's it. So in summary, to deal with the three-phase AC circuits, whenever you see delta, remove it. Remove it like what? Convert delta to I. Then deal with the circuits, converting three-phase to single-phase. After that, do your simplification. If there are some series elements, parallel resistors or impedance, do whatever you need. Okay? Any question? Okay, let me give you some challenges, some challenging examples. Like here, this circuit, we have only source and load. How about if there's some impedances in the middle? Again, there can be some series, some parallel element. Then you need to know how to do the conversion. So I'm gonna write in another sheet, like some challenging circuits that you need to think about. Assume we have, here is a source Y. That's connected to impedance here. Then I can say the load is delta. Let me just try to draw it this way. When you have this kind of circuit, what should I do? There is a delta, right? What should I do? Convert delta to I. Okay? That's step number one. So basically, Zy will be Z delta divided by 3. So let me redraw the circuit after converting delta to I. Okay? Then what should I do next? Convert three-phase to single-phase. Let's take phase A as a reference. So for example, oh, I didn't forget the neutral here. Uh-oh. The neutral connection. So I'm going to pick up phase A as a reference. That's phase A. So by picking up phase A as a reference, so here what I did, converted delta to I. Now I need to convert three-phase to single-phase by basically picking up phase A as a reference. It will be like this. Now, do you know how to find the currents? KVL, find the equivalents. So you need to find here Z1, here is Z2. So you can say IA equal VAN divided by Z equivalent, which is ZA, Z1 plus Z2, right? That's one scenario. Another challenging scenario. Let me give you a few seconds to write, then I'll go to another scenario. By the way, like in the quiz in Wednesday, we'll be in these kind of challenging things, okay? Like y, delta, convert delta to y, etc. Now another challenging scenario, which is, let me assume we have a y source. Every time I'm going to assume the source is y, so you don't need to worry about a delta source. Just worry about the load delta. Then I will assume we have like this. I think I was double C. Okay, we have something like that. How can we look at the circuits? Basically, nothing in delta, everything in y. What should I do? We need to find the per phase equivalent circuit. To find the per phase, let's take phase A. Let's assume this is phase A, for instance. Then so we can see these two impedances. I'm going to assume this as Z1, Z2 are in parallel. Okay? By following up. So in order to when you convert three phase to single phase, keep in mind that this will be in parallel. So here's a source. This is Z1. This is Z2. Then we need to calculate IA. This is VAN. Again, IA, which will be VAN over Z equivalence. What's Z equivalence? Z1 parallel with Z2. Okay? So just keep in mind, if you see these kind of weird circuits, don't get panicked. So it's fine. We can just handle it. Try to look at phase A. Start from one point and go back to the other point. Okay, any question? Again, keep in mind, you can do it more complicated than that. 2 elements series, 2 elements parallel, whatever. That's how we deal with this. Keep in mind, whenever you see delta, convert it to y before doing any simplification. Convert every delta to y, then you can say let's convert three phase to single phase. Okay, next lecture, we will go to the complex power on the three phase, which is called instantaneous three phase power. So let's stop here and